Okay. So for today, I just prepare. I can say that a review, a simple review through the object detection models, and I just wanted to show you what type of object detections model we have and we can use, and by that, for which application we select one of them or another one. Okay. So I will explain the models and so on, but don't hesitate to stop me if you have any questions and so on. So for the object detection, so the first question that comes in our mind, I don't know if all you are familiar and work with this or not, but the first question is coming that how does it work? So in fact, so we have the object detection. It's not something recent, so it's since 2001 we have such a this type of models, and we use it either with the image processing techniques or the deep learning networks. So for the traditional one that we use the image processing techniques, so we have some cons and pros for that. For the pros, so is that we don't need any annotated data. So we have the techniques, image processing techniques, and we applied it. We apply on the image, and we do the object detection by that. There is no parts of the training. So when there is no part of the training, especially in the supervised learning, I can say, so it means that we don't need annotated data. We don't need someone to do the annotation that is really time consuming and so on. This is really pros of that. But on the other hand, it's the technique, it's really limited or restricted to the multiple factors such as complex scenarios. So if you have complex scenarios, that would be difficult to go that. Occlusions, if we have this, or illumination, shadows, and so on. So these are the difficulties that people, scientists, think about to go more on the direction of using machine learning and especially deep learning to do the object detection. On the other hand, for the deep learning methods, the good thing about these methods is that they are significantly robust. You can use them for really complex things, and we don't have the problem of illuminations that much compared with the image processing techniques. On the other hand, for the deep learning methods for object detection, similar, this is the same problem when we use deep learning in general for classification, segmentation as well. So we need a huge amount of training data to train our model on that. If we don't have it, so that's a little difficult, or it's a little complicated to go on this. Of course, that I don't go in details, but we have some ways, transfer learning and so on, data augmentation to increase the number of data that we need. But in general, what we need a huge amount of training data, and I can precise annotated data, especially in this case of object detection in most of the well-known algorithms, because they are working on the supervised mode. If you wanted to go have a look at these algorithms, so I can say that we can divide these type of algorithms. So in the before, I can say that deep learning revolution or and after deep learning revolution. This is around 2014, 2012, and so on. Before that, so we had mostly we used some image processing, or I can say traditional object detection algorithm, such as, so if I can find my laser point, okay, such as Viola-Jones detector that was in 2001 at that time, and Still these days it's used a lot for detecting of face of the people. It's worked very well, and also for some simple objects, still violations can be used. Hog detector, histogram of a gradient, the algorithm that proposed in 2006, and still it's used for simple objects. And we have deform process model that proposed in 2008, and it was the first algorithm that introduced of a bounding box with the bounding box regression. So of course there are more than these three. What just I try to point at the three most popular one that still these days we use them. And then after deep learning revolution in 2014, there are a couple of algorithms proposed based on the deep learning. So starting from 2004, from regional-based CNN, convolutional neural network, SPPNet, then came to the 2015, the evolution of the region-based CNN, which came with the call fast RCNN, and then at the same year, faster RCNN. This is the evolution of the RCNN. And then in 2016, I can say that it was such a revolution inside the object detection algorithm by proposing YOLO that these days it's used a lot, and SSD. In 2017, we had Mask RCNN, Pyramid Network, RetinaNet. Then from 2018, we had the new versions of the YOLO, starting from YOLO version 3, then version 4. And today we have YOLO version 8 that introduced in 2023, almost in the beginning of 2023 in Janvier, or December 2022 or Janvier 2023. So, and that's much faster. So later in the comparison that we will see the comparison between them, and we will see where we can use one of them. Okay, but before going to do a comparison between them, this is something that we should have in our mind. So in the deep learning algorithms for object detection, we have two categories. So some of these algorithms, we call them one-stage object detectors. Some of them are called two-stage object detectors. What is the difference between what are the difference between these algorithms? One stage or two stages. So for the two stage algorithms, so we have one, we call it object region proposal. So the region that is proposed by that, and we have the object classification. That's in the second stage. Okay. So for the two stage methods, we have the highest detection accuracy. But on the other hand, as it is the two stage, it's a little slower compared with the one stage algorithms. And for, as I said, for the two stage object detectors, first we go on the region of interest to find the region of interest, and then on this region of interest we try to do the classification. Okay, so it's called finding region interest and the classification. So then it's come to the object detection. We say, what is this region? What is the class of this region? On the other hand, for one stage detectors, object detectors algorithms, so what we have, we do the prediction of the bounding box of an image without the region proposal step. So what we are doing, we eliminate this part. I can say in general, if you have seen the presentation of the YOLO, I think that I already did it. So you see that still we have the region proposal, but it's not like the one that we use in the 2D. So later we go on that to see a difference between them. So on one state object detectors algorithms, so they are super fast, really so fast. So we will see them together. But at some points not as good as the two stage algorithms, especially on recognizing irregularly shaped objects or a group of small objects. So in that case, so if we wanted to go and work on to detect small group of small objects or completely irregular shapes, so two-stage algorithms are recommended. I can say. So the main advantage of the single stage is that they are generally faster. So when we are working on the videos, so they can be used and we can get benefit of them as they are fast, especially on the real time object detections. If I wanted to put it graphically, the difference between between them. So for one stage object detection, so we have the image, it goes to the backbone, and directly from the backbone, so it can be VGG, ResNet, or any backbone that we have. It goes for the regression box. We do the regression box, so that from that we have the bonding boxes and the classification boxes that we have the object class. So which object is that? In the two-stage object detection, so we have the image, go to the backbone. On top of the backbone, we have the object proposal, and then we have the region regression box and the classification box to have the bonding box and the object classes. So graphically, this is the difference between the one-stage and two-stage object detections. If you wanted to have them separately, so
sorry.
Yes.
Just a small thing. Here it means any object detection algorithm starts with some kind of classification.
So actually, for the object detection,
so not the classification, segmentation.
Yeah, so here you mean
no, at the beginning, VGG ResNet. It means
so
first
actually,
step is
actually, this is the architecture. This is the convolutional network.
Yes.
It's not. We cannot say classification because we don't use them for the purpose of classification. Yes. We use them for the purpose of feature extraction.
Yes.
Because if I wanted to, maybe I can show it later. When we use the CNN in general, we have one part that is called feature extraction that consists of the all convolutional layers.
Mm-hmm.
And then we have the one parts of the classification that we have the fully connected layers plus softmax.
Yeah,
so if we use this, so this is for the purpose of the classification. But here as a backbone, we have convolutional layers. So these convolutional layers extract just features. So it's not classification. So here we have the classification of them because we put the softmax and we say that on this region, which class is that? But here is just feature extraction. Is it your answer?
Yeah.
Okay.
Yeah, perfect. Okay.
So if you wanted to categorize them, so we have the one-stage algorithms, the family of the YOLO. So I can say that YOLO, the simple one that came, and then YOLO version 3, 4, 5, 6, and today 8. STD and RetinaNets are the type of the algorithms that we call them one-stage algorithms. And RCNN, the family of RCNN, such as fast RCNN, faster RCNN, plus mask RCNN, and GRCNN, pyramid networks are the type of algorithms that we call them two-stage algorithms. If I wanted to have a look on that, so I think in the video of there you have seen the structure of the YOLO, so I don't go on that. But if you want to go and show you an example of the two-stage object detection algorithms, so I can go for the evolution of the RCNN. So the first algorithm that came, regional-based CNN, so RCNN, we had some regional proposal on the level of the image, and then for each of this region we gave it a convolution, and we did the classification and bonding box regression. So we had this region, we had this region, we had this region, and then resized all of them to the same size, and we gave them to the convolution. It was good at the time, but it took a time to do the classification, to do the object detection. So that was not good for real-time application. Then a year after, so they propose another, I think a year or 2 years after, 2 years after, so they propose another one. So they just change the algorithm. Instead of first finding the region and then give each region to the convolution, separate convolution. So they use the convolution networks, so the backbone that you saw there, and they extract features. So we have the feature map here. The output of convolution, we have the feature map. And in the feature map, we had regional proposal, external, I can say the external regional proposal method. And these external region proposals go to the fully connected layers to do the classification by the softmax and the bounding box regression. Then as a last series of this family that came as a faster RCNN, so they keep almost the same structure, but here when they extract the feature map, okay, they don't do any decision at this level. So they use something that is called regional proposal networks, okay, to propose regions for them, and then they go to the region of interest pooling, and then based on that they go for the classification. So this is what we call evolutions of RCNN, from the RCNN to the faster. That is the one that today everyone use it because it's fast and can be used on the real time. Here is a comparison between them. So on left we will see that yellow version 2. So that it's used on the COCO database, yellow version 3. So here we have the frame per second, but it's not visible, sorry. Mask RCNN, and we have also I can say the deep lab version 3, another one that I didn't talk a lot on this because it's more on the segmentation. We don't have the bounding box that much here. And then the recent one, yellow version 3, that is so fast, and it's used for object detection and tracking. This is something that it's used, and it's really useful. So you see, so it detects the cars here, and then it go for the trajectory. So it's go tracking of them, and that's something that can be used as well. If, for example, we have some data that we wanted to, on the real time, we wanted to detect them and also track them. And you see that frame per second is 9 frames per second. That's the good speed on that. If you wanted to compare them numerically, so in the means of the accuracy or so on, so usually as a benchmark, the popular benchmark for these algorithms are the Microsoft COCO. So this is what we saw also on the videos on that. And when we wanted to compare them, usually the metric that we use for them is the mean average precision. That's probably the map. Is there any question? Actually, as I don't have Skype on here, I don't know if someone wrote a message.
It's okay. It's okay.
Okay, sorry. So we have the mean average precision as a metric that we compare the object detection algorithms, and here is an example of them, that we have the box average precision, and here we have the dates that they compare it. So from the so in the gray we have the other models, because as I said, so I just named some important and well-known models, but we have several models on that. And we have the models with the highest box average precision. So from 2020, so it goes for the DETR and the former DETR, SWIM, and so on. So it's to the ConvNex, and yellow version 7. That's today it's the, I can say that before, because this comparison have done in 2022. So we then had the yellow version 8, but the period, so yellow version 4, it was the one that gave the highest average precision. And for the check if the fastest real-time object detection algorithm on the inference, we call it as the inference time. So we have the algorithm as the faster RCNN in 2022, in 2020, and then coming to the 2022, we have still YOLO version 7. Also, we have the variety of the YOLO, like the YOLO E and so on. These are the one, and on the left we have the frame per seconds. Another comparison of them on the Coco mean-val for validation. So we have the average precision on the minival on the percentage, and we have the inference time as a millisecond. So of course that when it's close to 1, it's better, and when it's go up, because it's the average precision, it would be better. That's obvious. And from them we will see that yellow version 7 is the one that it's much faster, and we have the good accuracy on that. But if the fastness is not the case, at some point we can use also other type of algorithms. Okay, other version of that. So, for example, like YOLO X, YOLO version 5, and so on, or faster RCNN. Still the average precision is less than the yellow that's proposed these days. It's very, very common. That was